So I realised as Sarah and I put this together that we've crammed a lot in. So I'll try to keep moving through it so we can get through the show. Alrighty. So what I'd like to do today is give you an overview of what's really a set of projects that Sarah McCord and I are coordinating at the Jornada with our Jornada colleagues, as well as collaborators across the ELTAR wind erosion and rangeland soil erosion working groups, and increasingly with the indicators group, and more broadly with our collaborators at NRCS, BLM, and across USGS. And as Brandon said, this work's really about looking at how we can link erosion prediction models and assessments to available indicators of ecosystem attributes and services through big ecological monitoring datasets. The set of projects that I'm going to talk about have sort of 5 broad objectives, and these are to enable discovery and use of indicators of different ecosystem attributes and services across spatial scales, to develop erosion prediction tools that can leverage monitoring data sets that are producing these indicators so that we can value add to them, to facilitate access to standardized calculated and modeled indicators, and then from there link those indicators to ecosystem dynamics through decision support tools like ecological site descriptions. And in doing so, sort of achieve our 5th goal, which is to link these indicators to management across scales. And in doing this, support identification of conservation practices, as well as assessment of the effectiveness of the practices that we're implementing across our landscapes. And this work has a bit of a soil erosion bent. That's a keen interest of mine. And the reason that we're looking at soil erosion is really because of its environmental impacts, its effects on landscape formation, and its influence on Earth system function, particularly through interactions with biogeochemical cycling and climate, which often feed back to the environmental impacts and landscape formation. And together, these all influence the different components of sustainability that we're interested in across ELTAR, including the environmental and productivity components, as well as the resilience of our landscapes to climate stresses and different management practices, and rural prosperity, including health and well-being of our communities. At the moment, there are a number of deficiencies in sort of our current assessment capabilities for looking at wind erosion and water erosion. And these include that erosion assessments really haven't been well integrated with assessments of other ecosystem services across rangelands. We don't really have many well-established connections between management and rangeland erosion, particularly wind erosion, where there's been sort of less research attention over the years. And air and water quality impacts downwind and downstream haven't really been well connected to upland erosion. And so this is something that we'd like to address. If we can address these challenges, then there are going to be a number of pretty large benefits of linking erosion estimates to ecosystem services. And some of these include ensuring that we link these key processes that are modifying land potential to the decision support systems that we're using to inform management of rangelands. We can ensure that our assessments are more inclusive or holistic of different ecosystem services and their responses to management. And we can ensure that we can make sort of more holistic assessments and identification of land use and management practices to support sort of long-term sustainability of our agroecosystems, as well as intensification in areas where that's possible and appropriate. So all of these sort of benefits need to be considered in the context of we have really diverse land uses and stakeholders across the Western rangelands, and they're sort of illustrated on the maps here. And livestock production by private ranchers really is dependent on public lands and lands that are administered or in which management is supported by various agencies, including the Bureau of Land Management and National Park Service, which actually have allotments within national parks supporting grazing. So in order to sort of look at the status, condition and trend of our rangelands, these agencies and producers need consistent indicators and methods to measure and monitor those indicators. And over the last sort of few decades, Jornada scientists have been working with these stakeholders to identify consistent indicators for different ecosystem attributes. And the high-level attributes that they've been focusing on include the biotic integrity of the systems, soil and site stability, and the hydrologic function. Through sort of participatory processes involving a few hundred individuals, so these are private producers, agencies, and folks in academia, we've developed a sort of a five-step approach to identifying consistent indicators. And these really focus on sort of different structural components and functional relationships within the ecosystems. And the steps look at defining indicator selection criteria, identifying a broad initial list of indicators that we could use, rating criteria that we want to assess those indicators with based on their performance, rating the indicators against the criteria, and then developing and applying a system for integrating the criteria ratings that take into account the different interests and values of the various stakeholder groups. So having identified sets of indicators, they then established a sort of set of criteria for identifying methods that could be used to monitor these indicators. And preference was given to methods that were well documented, already widely used across the range community, were easy to implement and had a minimum potential for bias. And this ultimately resulted in adoption of standardized core indicators and methods that are described in the monitoring manual for grassland, shrubland, and savanna ecosystems. And that was put together by Jeff Herrick and colleagues. And there are four key methods that are described in this manual that have been adopted by various agencies, including the line point intercept method, vegetation height method, and gap intercept method, which all run along transects at the plot scale, and a plot scale species inventory. And together these methods have been implemented by various agencies, including ARS in research projects, using often sort of scalable, spatially weighted sample designs at over 60,000 plots across grazing lands in the US. And most of the concentration of that monitoring effort, or those monitoring efforts, have been in Western rangelands. So the indicators that we can get from these monitoring programs describe different attributes of the ecosystems, but they don't explicitly describe erosion processes. So we've been looking at how we can value add to these indicator sets, leveraging various indicators that are being collected, describing sort of site susceptibility to erosion through soil properties and vegetation structure. And the Rangeland Hydrology and Erosion Model, or REM modelling team within ARS have already demonstrated an approach to developing an erosion model that can leverage these indicator data sets. And at the Jornada over the last 8 years, we've been following a similar approach, developing an aeolian erosion model, or AERO, which can simulate sort of site-level wind-driven sediment fluxes and dust emission using these indicators from these monitoring data sets. This slide sort of illustrates the workflow that we're following with AERO development and implementation, and we're working REM into this as well. The overall sort of approach or strategy is to use a small network of research sites to leverage these big monitoring data sets. So we have our standardized monitoring data sets on the left there. In 2014, we established the National Wind Erosion Research Network as part of LTAR, and we use those sort of really intensive research observations from the small number of network sites to support model development. We can then implement AERO on SciNet to the large monitoring data sets, produce plot scale estimates of sediment fluxes, which are indicators of site stability or instability, and particulate matter emissions. So these are indicators of air quality and soil and nutrient losses. And we're then looking at how we can interpret these erosion estimates or indicators across different spatial scales in the context of other ecosystem attributes that we can obtain from these indicator data sets and feed those into LTAR research, as well as tools and analyses to support our stakeholders. So to do all of this, we're developing what we're calling a landscape data commons, which is illustrated here. The idea of the data commons is that it allows us to bring together different standardized monitoring data sets This includes aggregating existing monitoring data sets like BLM AIM data and NRCS's on-site grazing lands NRI data. We're also a repository for the National Wind Erosion Research Network data. The Data Commons aggregates these data sets, tidies them up, enables us to calculate standardized indicators of various ecosystem attributes from them, as well as inputs to erosion prediction models. In doing this, we link the monitoring data to external databases so we can bring in other soil and plant information. And then the idea is that from there, we can link the erosion estimates with the other indicators out to stakeholder tools like ecological site descriptions in the ecosystem dynamics interpretive tool, and provide that information to users on the ground through mobile apps and that kind of thing. So at the sort of core of the Data Commons is an R package that Sarah McCord has developed. This enables us, it's called Terradactyl, it enables us to aggregate the different monitoring data sets, get them in a tall, tidy format, and from there it has a set of core functions that correspond with the different monitoring methods that enable us to calculate consistent and standardized indicators, as well as custom indicators across the various monitoring data sets. And this lets us look at things like species occurrence with different functions. So if we have questions about biotic integrity, livestock, forage, and wildlife habitat, we can use those functions. We can also use Terradactyl to produce inputs to the AERO model, as well as the REM model to look at wind and water erosion. So when we sort of run through this process, we're able to apply these erosion prediction models to these monitoring data sets. The maps on the left here show an example of the AERO application to about 30,000 AIM and NRI plots, with about 1,000 in New Mexico here. AERO estimates include total horizontal sediment flux, so this is our indicator of sediment moving across a landscape at the plot scale, as well as particulate matter emissions like PM10 and PM2.5 that are regulated under the National Ambient Air Quality Standards. So a challenge in producing all of this information is how do we interpret it? And so to do this, we've been looking at how we can link the erosion estimates into ecological site descriptions that are used by managers across public and private rangelands to support management. So a focus of this work has been interpreting our model estimates and the various other indicators from these data sets in the context of the ecological land resource hierarchy, starting with a focus on sort of what's going on at the ecological site scale. So by using ecological site descriptions with their state and transition models, we can start to understand how various indicators of these ecosystem attributes and soil erosion rates vary or might change with ecosystem state changes, and how management might be influencing those changes, and what conservation practices might be most appropriate for addressing erosion concerns or other concerns in this ecological site context. So using the models, we can sort of start to look at what are potential distributions of sediment transport or erosion rates for different ecological sites in a landscape. And by developing quantitative keys to key our monitoring plots to ecological sites and states, we can start to assess how changes in different attributes of the ecosystems might respond to ecosystem state changes. So we can look at various indicators that are driving erosion, for example, like the amount of bare soil at a plot and the structure of the vegetation, and we can assess what potential erosion responses might be. So by looking at sort of more quantitatively at distributions of our various indicators across ecological sites and states, we can start to identify where there might be structural thresholds of concern that we could use as benchmarks to support monitoring and assessment of the effectiveness of our management practices in landscapes. And we can, of course, then interpret how erosion rates might be responding to changes in management that might tip a certain landscape over our benchmark. So by using these process-based models, we can also look at where there might be functional thresholds for erosion and whether or not these are generalizable across different ecological sites and states as they respond to different management practices. And by bringing the different monitoring data sets together, we can also establish a regional context and temporal trends for the changes that we're observing at finer scales, say at an ecological site scale or at the scale at which a management practice has been implemented in a landscape. So the example here just shows some potential distributions of PM10 emissions across 4 different MLRAs in New Mexico as they're varying over time. As we get more data, we can start to fill in these distributions and better link them to different indicators of ecosystem attributes and services. We also use these data to start to address sort of broad scale questions about how different disturbances or changes in our landscapes are influencing erosion processes and responding to management. In the Rangeland Soil Erosion Working Group in LTAR at the moment, we're developing a project looking at how wind and water erosion might be responding to invasive plant species across the West. And this project's leveraging these different monitoring data sets through the Landscape Data Commons. So bringing all this together allows us to provide a lot of context for local and regional scale resource concerns and analyses that we might want to run. So the different monitoring data sets can provide regional context for local resource concerns. So as an example, air quality over national parks is likely impacted by grazing on surrounding private and public lands. We can use the monitoring data sets to make an assessment of erodibility of these landscapes and potential dust emissions that might be impacting air quality downwind. We can also establish local context to support more regional assessments. So thinking about grazing management on these private and public lands, we might want information about sort of reference conditions to support benchmark development for our assessments. There may be few reference sites on these more heavily used lands, but we may be able to get information on that from national parks that may be less disturbed. We can also use the data to fill gaps. And an example of this that we've been working on with the National Park Service is their Northern Colorado Plateau monitoring network wanted to assess wind erosion, but at that time they weren't collecting vegetation height data on their monitoring plots. So by bringing together the different monitoring data sets, we were able to establish distributions of vegetation height by species based on the regional data, and use those to drive the AERO model to inform more local scale assessments. So another real benefit of bringing these indicator data sets together is our ability to establish more robust benchmarks to support assessments of the efficacy of different management strategies or practices. Radar plots like the one on the left here really help us visualize the performance of systems against different indicators. But what we really want to know is whether the performance of certain management systems or practices against an indicator is meeting our management objectives. If we're looking at a set of practices, do they all meet our objectives? Do they all fail to meet our objectives, or do some meet and some fail to meet our objectives? So by drawing together these large indicator data sets, we can assess how a practice in a management area, like a grazing allotment, might perform relative to a benchmark that we could establish based on knowledge of how the system functions or requirement, for example, for wildlife habitat, or from distributions of available indicators that we can get from these monitoring data sets. So in the example here, we might have a management objective of maintaining pronghorn habitat by ensuring average woody vegetation height is not greater than a certain amount. And by assessing our local data for our experiment or our management area against these broader scale indicators, we might be able to assess that practice or that area is failing to meet or meets that benchmark for habitat suitability. And we can apply this approach to the other ecosystem attributes and erosion processes that we can obtain from these large monitoring data sets. And this approach is something that we could really leverage across LTAR, using these regional monitoring data sets to provide broad context, as well as local context to support more quantitative frameworks for assessing our management practices and systems that we're wanting to evaluate, and whether or not those are meeting our objectives for sustainable intensification. So I'll sort of finish up looking at bringing all of this together. We're trying to develop some different decision support tools for our stakeholders. One of these is an online data portal for the Landscape Data Commons, in which will enable users to interact with the different monitoring data sets at different levels, including providing analysis tools like an ecological site summary tool that enables users to summarize indicators at different scales, including ecological site scale. And we currently have a project with NRCS looking at how we can incorporate these different indicators and model estimates into ecological site descriptions in EDIT. And the sort of diagram here illustrates the workflow that we're starting to develop. So we've linked our erosion prediction models to the Landscape Data Commons and the various other indicators in there. And we're now looking at how through coded ecological site keys and APIs, we can link the monitoring indicators to ecological site descriptions, providing users with sort of dynamic graphs of various indicators, enable them to visualize where ecological thresholds of concern might be associated with state changes, as well as developing a simple sort of traffic light system to show which sort of vegetation states within an ecological site might have an erosion concern and which conservation practices might be most appropriate for addressing that. So I'll wrap it up here. We've learned a large number of things in developing this work. The points I've got here are maybe fairly obvious, but they're quite important. To assess our management objectives and trade-offs, we really need data, and those data need to be scalable. But we need infrastructure that enables data integration, data aggregation, use and reuse. That has been a real challenge in bringing these different monitoring data sets together. And we need to be able to link these data and indicators to models, enabling us to assess various indicators that aren't otherwise monitored. And most importantly, perhaps we need frameworks for interpreting the indicators and making them accessible to our stakeholders. And this is something where I think there's a lot of opportunity right across LTAR through different working groups, including the Indicators Working Group, to really contribute to. So I'll leave it there, and I'm happy to answer any questions, and I think that Sarah might be on the line as well, so she may want to answer some questions too. Thank you.